Today's topic is cooling by adiabatic demagnetization of paramagnetic substance. We will see how cooling is produced by adiabatic demagnetization of paramagnetic substances. We will discuss the experimental method to obtain low temperature by this theory, and we will find the expression for cooling on the basis of thermodynamics. First, we will see the theory behind the cooling produced by adiabatic demagnetization. Debye and Geik told that when a paramagnetic substance is magnetized, then its molecules, which behaves as magnetic dipoles, are aligned along the direction of magnetic field. For this, work is done on the substance which increases its internal energy, so temperature of the substance increases. Now, if the substance is demagnetized rapidly by adiabatic process at low temperature, then the temperature of the substance decreases. In this process, work is done by the substance, which reduces its internal energy, and hence the temperature of the substance decreases. This phenomena is known as magnetic caloric effect. The lower is the initial temperature of the substance, decrease in its temperature is more. Experiment performed by Simon and Courteau to produce low temperature by using above theory is illustrated in this figure. P is a paramagnetic substance placed in a glass tube A. This is the figure which shows the experimental arrangement to produce low temperature by adiabatic demagnetization of a paramagnetic substance. In this figure, P is paramagnetic substance. This paramagnetic substance P is placed inside a glass tube A, and this glass tube A is placed inside Dewar flasks B, C and D. In Dewar flask B, liquid helium is filled. In Dewar flask C, liquid hydrogen is filled, and in Dewar flask D, liquid air is filled. So, P is the paramagnetic substance. It is placed inside a glass tube A, which is surrounded by Dewar flasks B, C and D, which have liquid helium, liquid hydrogen and liquid air respectively. Entire apparatus is kept between two pole pieces and S of a strong electromagnet. These are the two pole pieces, North Pole N and South Pole S of a strong electromagnet. So this entire apparatus is placed between these two pole pieces N and S of a strong electromagnet. These two pole pieces N and S will produce a magnetic field which will used to magnetize the substance, to magnetize this paramagnetic substance P. First of all, helium gas is filled in tube A, by which the substance becomes in thermal contact with liquid helium and its temperature becomes 0.8 degree Kelvin. In this glass tube A, in which paramagnetic substance P is placed, first of all, we filled this glass tube A by helium gas. By filling the helium gas, this paramagnetic substance comes in thermal contact with this liquid helium, which is filled in Dewar flask B. Glass tube A is inside the Dewar flask B, in which liquid helium is placed. Liquid helium have low temperature of 0.8 degree Kelvin. So when helium gas is filled inside this tube A, this paramagnetic substance P comes in thermal contact with this liquid helium and its temperature becomes equal to that of liquid helium, that is 0.8 degree Kelvin. By applying magnetic field of 1 Tesla, now we apply this magnetic field of the order of 1 Tesla, then the substance becomes magnetized and its temperature increases. Heat produced is given to liquid helium by helium gas and temperature of the magnetized substance again become 0.8 degree Kelvin. When we apply the magnetic field by the electromagnet, the temperature of this paramagnetic substance will increase, but it is in thermal contact with liquid helium, so it gives heat to liquid helium, and after some time its temperature again become 0.8 degree Kelvin, that of liquid helium. Now helium gas is removed from the tube A by vacuum pump. This glass tube A is connected to vacuum pump, and with this vacuum pump the helium gas is now removed from this tube A, and now this paramagnetic substance P is demagnetized. The magnetic field is removed suddenly, rapidly. So now the temperature of this paramagnetic substance will be decreased. This process is adiabatic process because helium gas is now removed from tube A and paramagnetic substance is placed inside a vacuum. So this is the process of adiabatic demagnetization. Magnetic field is removed, the material paramagnetic substance P is demagnetized. In this process, the work is done by the paramagnetic substance and its internal energy decreases, hence its temperature also decreases. This reduces its temperature to 0.25 degree Kelvin. To determine the temperature of the substance, a coil is wounded around tube A and magnetic susceptibility chi is determined. To determine the temperature of the paramagnetic substance, this coil is wounded around tube A, which is shown by the circles around tube A, 3 circles on left and 3 circles on right. These represent the coil wounded around tube A, and by this coil we find the magnetic susceptibility chi, and from Curie's law this chi is equal to C upon T, where T is absolute temperature and C is constant, which is known as Curie's constant. So by using this Curie's law, magnetic susceptibility chi, which is equal to C upon T, this gives the temperature T. By using some alums like chromium, aluminium, alum, low temperature up to 0.004 degree Kelvin can be produced. Now we will find the expression for cooling. If magnetizing field H is applied to a paramagnetic substance by which its intensity of magnetization M increases by dm, we consider magnetizing field capital H. When this magnetizing field capital H is applied, intensity of magnetization, which we write by capital M, this intensity of magnetization capital M is increases by dm. So by applying magnetizing field H, intensity of magnetization M increases by dm. In this process, work done by external magnetizing field will be equal to H dm. H is external magnetizing field and dm is increase in intensity of magnetization. So work done by this magnetizing field H is equal to H dm. So the work done by the substance will be equal to minus H dm. Work done by the substance we write dw, it is equal to minus H dm. Since H dm is the work done by magnetizing field on the substance, so work done by the substance will be negative of it. dw is equal to minus H dm, and we know that if volume of a gas increases by dV at constant pressure P, then work done by the gas is given by dw equal to P dV. If we compare these two equations, dw equal to minus H dm, it is equation 1, and dw equal to P dV, it is equation 2. If we compare these two equations, then we see that we can replace P by minus H and we can replace V by M. dw equal to minus H dm and this dw is equal to P dV. So we will write minus H for P and M for V. Comparing equation 1 and 2, it is not 2 and 3, it is 1 and 2, we see that if we replace P by minus H and V by M, then we can use the laws of thermodynamics to paramagnetic substance. In Maxwell's thermodynamical relation, we will use this Maxwell's relation. Delta T upon delta P at constant S equal to delta V upon delta S at constant P. Remember, the Maxwell's thermodynamic relations are relations between four thermodynamic variables. These four variables are P, V, T and S. If we write these four variables in alphabetical order, then this order is PSTV. Look at this thermodynamic relation and read in this order PSTV. Then PS is in denominator from left to right and TV is in numerator also from left to right. So write in this order PSTV, PS in denominator, TV in numerator. In left hand side, it is partial differentiation with respect to P, and in right hand side it is partial differentiation with respect to S. So when we have partial differentiation with respect to P, we write S constant, and when we write partial differentiation with respect to S, then we write P constant. So we will use this Maxwell's thermodynamic relation, and in this relation now we replace these two things. We replace P by minus H and V by M. Then we get this relation. Delta T upon delta H at constant S equal to minus delta M upon delta S at constant H. In right hand side, now the left hand side is delta T upon delta H. We want to find delta T, change in temperature. Since the cooling is produced, so we want to know how the temperature is reduced. So we want delta T, change in temperature. And we are demagnetizing the substance, so magnetic field is changed. So we want delta T with respect to delta H. How change in delta H will affect delta T. In right hand side, we divide by delta T in numerator and denominator and get this equal to minus delta M upon delta T at constant H divided by delta S upon delta T at constant H. And now multiply by T in numerator and denominator, so that in denominator T delta S will become delta Q. From second law of thermodynamics, dQ equal to T ds. So we write T delta S equal to delta Q in denominator, so that this delta Q upon delta T will become a specific heat, and it is M into CH. CH is a specific heat. So delta Q upon delta T is mass into specific heat. And now specific heat C is written as CH because it is specific heat at constant H for constant magnetizing field. From the definition of specific heat, we have dQ equal to mc dt. From the definition of specific heat, which comes from this relation dQ equal to mc dt, we have C equal to 1 upon m dQ upon dt. So we write CH as 1 upon m delta Q upon delta T at constant H, So we have delta Q upon delta T at constant H equal to mCh. So we write this denominator equal to small m Ch. Ch here is specific heat at constant H. Now delta T upon delta H will become equal to minus T upon mCh delta m upon delta T at constant H. Magnetic susceptibility chi is defined as m upon H. H is magnetizing field and m is intensity of magnetization. So magnetic susceptibility chi is the ratio of intensity of magnetization and magnetizing field. Chi is equal to m upon H. It is the definition of chi, which is magnetic susceptibility. And from Curie's law, this chi is equal to C upon T. It is proportional to 1 upon T, and C is constant known as Curie's constant. So definition of chi is chi equal to m upon H, and from Curie's law this chi is also equal to C upon T. From this equation we write m equal to Ch upon T, and from this relation we can find this partial differentiation delta m upon delta T at constant H. As m equal to Ch upon T, so delta m upon delta T at constant H is equal to minus Ch upon T square. Ch are constant and differentiation of 1 upon T is minus 1 upon T square. So we write this value of delta m upon delta T at constant H, which is equal to minus Ch upon T square, and now we have delta T upon delta H at constant S equal to minus C upon mCh into minus Ch upon T square. Now there are two C here. One we write as C, capital C, which is Curie's constant, and other is Ch. This Ch is specific heat at constant H. So this becomes equal to C upon mCh H upon T. Now we write the term of T with delta T and term of H with delta H. Take this T to left hand side, so it becomes T delta T, and delta H from left hand side we take it to right hand side, so it becomes C upon mCh H delta H. Now integrate this equation. In the process of adiabatic demagnetization, magnetic field is reduced from H to 0. We are demagnetizing the substance. Magnetic field is removed. So magnetic field is reduced from H to 0. And then if we assume that temperature changes from T1 to T2, then if we integrate this equation, we get integral T delta T equal to C upon mCh integral H delta H. In left hand side it is the integral with respect to T, and values of T are changes from T1 to T2. T1 is initial temperature and T2 is final temperature. In right hand side it is integral with respect to H. So the limits of H are from H to 0. Initially magnetizing field is H and finally it is removed, so it is 0. If we integrate, then integral T dt gives T square upon 2, and with this limit it becomes 1 upon 2 T2 square minus T1 square, In right hand side we have C upon mch, and integral h dh becomes h square upon 2. If we put the limit from h to 0, then it will become minus h square. 2 is cancelled out in left hand side and right hand side, and we have t2 square equal to t2 square minus t1 square equal to minus ch square upon mch, or t2 square equal to t1 square minus c upon mch h square. In right hand side, take t1 square common. However, it is not common in both the terms, but we take common t1 square. So it will become t2 square equal to t1 square into 1 minus c upon mch h square upon t1 square. Or if we take its under root, then we find the value of t2. t2 is equal to t1 and under root of 1 minus c upon mch into h square upon t1 square. It is clear that t2 is less than t1. t2 is less than t1 because we have in right hand side t1 into 1 minus something.